Alright, welcome to the second part, repeat class for February 4th. I keep saying, may the February 4th be with you, so it's almost a Star Wars. I almost said Star Trek Day. Every month is almost Star Wars Day. Controls 2, CNTL3020. Fenchurch College, London, Ontario, 2026. Let's go. All right, so this is the review before the test. Now, when it comes to what is going to be on the test, there will be I might ask you all questions about everything that we have done so far. So it will be similar questions that what you had on the quiz, except you're going to have the formula sheet provided to you. Or you can bring your own sheet, but on that formula sheet you can only have the formulas, the explanations of what the letters mean, what the designations mean on the formula, and that's it. No, nothing else. It is your thing to know how to use the formula and which formula to use. So I'm going to prepare a formula sheet for you. I can hand it out. You can bring your own formulas, you can use yours, you can use mine, or you can use both. And as far as what you bring to the test, bring a pen or pencil and a calculator. And if there's any scrap sheets that's needed, I'm going to provide them for you. The only thing I'm going to ask when you hand that in, I'm going to ask you to what am I going to ask you to? Hand in everything, including the formula sheet that you had, including my formula sheet, and all the sheets that you have used. If you have used some scrap papers to jack things down, just put those in as well. Okay. And the test is going to be on Monday, next Monday, which is that 2-hour session that we have. If there's anyone that needs to write the test or chooses to write the test in the testing center, it's up to you to contact the testing center, and then the testing center contacts me. They're going to ask me for a copy of a test, and I'll do all that. But just I think you know the drill by now. This is not your first semester here, right? All right, the review. I'm going to review the Pascal's law mostly because that's the most intense as far as calculations and the logic that goes with it. I might ask you some multiple choice questions. I will ask you certain questions that you have to come up with an answer with no any multiple choice. You just have to know the stuff. And I will ask you, I will give you some questions that you need to calculate certain things. So all the other stuff is posted. You just read it. I might also ask you things from the lab. I might give you a symbol, and I'm going to ask you what it is. Is it a 3 two-way valve? What does it mean that it's a 3 two-way valve? What kind of actuation? Is it a solenoid? Is it push button? Is it a momentary push button? Is it maintained? That stuff I might ask you. That has to do with the labs. Not going to give you any questions that have to do with the 2-wire/3-wire system, because we have done it. You have connected that, and you're really good at it. Although I haven't given you the whole details on what makes it 2-wire, what makes it 3-wire, so we'll take care of that. I'm just going to throw that question for you, because we still have one more lab that has to do with that, which is this week's lab. So just leave it for the next test as far as that. And that's pretty much it. If you have any questions regarding what's going to be, as far as the test, I'm pretty sure I covered that all right now. Right? All right, review. As I said, this is just because I only review the calculating things, the calculations with you. doesn't mean that's the only questions I'm going to ask you. Anything that's posted and we talked about, we experienced, will be test material. Okay? So just read those post-it notes, go over them, make sure they make sense to you. All right, so the most intense part is the numbers that we have to deal with. And there it is, it works. All right, the Pascal's law, that's the thing that evolves around everything that we do. It evolves around Pascal's law. Core concepts that we know, we have core concepts you must know. All right. We just make sure that we are recording. I always get paranoid with that because I don't want to lose the session here. Yes, we are recording. Okay. Core concepts you must know. What is a fluid? A fluid is a substance that continuously deforms when a shear stress is applied, has no fixed shape, takes the shape of the container, can flow freely. That's the key concept of one of the questions that kind of check-up questions a few slides down the road. The particles can flow freely because of the weak particle bonds, and it has to do with how the pressure forces are distributed with reference to, as opposed to solids. Okay? Grade 12 physics, maybe. All right, included, good review for us. Liquids, water or oil, when it comes to the fluid power that we're using. Gases, air, steam, those are examples. Other gases might be as well used, but for the most part, the stuff that you're going to be dealing with when you go to work is probably going to be air for the most part. If there is some specific situations in some medical lab that certain things need to be accomplished, then you may use another gas. Plasma, ionized gas. I'm not going to get into what ionized gas is, but it's a gas. This is not a chemistry class. It's a gas. Fluid power. What's a fluid power? So these are the key concepts that we're dealing with here. Fluid power is the use of fluids to transmit force and motion. And in our cases, what we deal with is, when it comes to fluids, we're talking about hydraulics, which is liquids, and they're described here as nearly incompressible. But to make things simple, we say that, to simplify things, we say that liquids are incompressible. All right? Now, pneumatics use gas or gases, and gas or gases are compressible. And both hydraulics and pneumatics, they evolve, they rely, with the exclamation mark here, on Pascal's law. All right, Pascal's law, exam critical, very important, critical. Right, hold on. Now here's a big mistake. I didn't catch it, but we're going to correct that. Statements of the Pascal's law. Pressure applied to a confined fluid is transmitted undiminished in all directions, and the pressure acts equally on equal areas. It's equally on all the areas. So let's just fix this here. All right. All areas. That's better. Okay. And here's another big mistake here. I didn't catch it. This thing here. No. Pressure equals force over area. How can we tell? Check the units. The units, in square brackets I always put them. We have a unit for pressure. That's a PSI. What does that stand for? Pounds per square inch. All right, pounds per square inch. So that now we have fixed that one here. Where P, and usually pressure we designate it with a small p, because quite often or usually the capital P is reserved for power. So F is the force, A is the area, and what we have here, force, the units of measurement. The units of measurement here with the metric, we got newtons, meters, pascals, atmosphere, and bar. And for the imperial, we got pounds, we got square inches, we got pounds per square inches, and we got atmosphere. And the atmosphere, the equivalent in the imperial system would be the 14.7 pounds per square inch gives us 1 atmosphere. Can you tell me what 1 atmosphere is? Can you feel it? Can you experience that? We are sitting in it all the time. We are in the atmosphere. And 1 atmosphere is the pressure that is at the sea level. And wherever you are on the planet, you might experience a little bit higher pressure, a little bit lower pressure. When the pressure gets a little bit lower, then we don't feel well. It's raining, usually it will be rain, and there'll be a bad weather. If the pressure goes a little bit higher to maybe 102 kilopascals, because 1 atmosphere is equal to 1 bar, or it's also equal to 100 kilopascals. So the pressure goes to like 95, 98 kilopascals, then we feel bad. That's about bad day for us. Some people get headaches and And it's always raining. Not always, but you can expect the rain or bad weather. When the pressure goes a little bit higher, 1 or 2, like 102 kilopascals and all that stuff, then the weather is nice. High pressure moving in, low pressure moving in. Weather reports. When you watch TV, you get that. All right. So that's something that I just want to give you something that's tangible for us as far as our understanding of things. Okay. So that will be the units here. We're going to come back to some of that. You might jot it down on your formula sheet as well, but I'll give you some more stuff. Continuing the review before this test, work and energy. There is no free energy. So as I said to the other group, all the YouTube videos that sometimes you can see, the click collectors, not sure why they do that. Those things should be scientifically banned from being shown when somebody shows, here is a perpetual motion. Look, I just connected this thing to the other thing and I just put things in motion and it just powers itself, and it doesn't. All right, so I'm pretty sure you know already that that's the case. There is no such thing as perpetual motion. Actually, there is a perpetual motion as far as thing to say. All right, a terminology. It's a term, ideal term. Practically, it doesn't exist. We always have some losses. So, in order for things to run continuously, we have to continuously supply power, because we do have losses. All right, so definition of work, scientific definition of work. Work is done only if a force causes a displacement in the direction of that force. There's another thing here that sometimes in science is being included, which is, if I can find my little dot, that will be times the cosine of the angle. Well, if you are moving a block of wood, and if you apply this force, and the block is going to move this way here, the angle between the force applied and the movement, the displacement, there is no angle, they're aligned. The angle between them is 0, and we all know that cosine of 0 degrees is 1. Right? Same as sine of 0 degrees equals to 0, and that's how we make the sine wave, right? All right. So where's my pen here? So when we displace, here's my pen. I found it. And when we place that, but if we have a railroad, here, that's bad railroad. Okay, and there is a steam engine on that, or is a cart with the wheels. If we give it a push this way here, that thing is still going to move that way. So now we have an angle. So then you have to include that. However, when we're dealing with cylinders and a closed system, hydraulics or pneumatics, but mostly in hydraulics when you come to do that, it checks out. It's more useful in applied hydraulics rather than pneumatics, but it also works with pneumatics. So we have, let's say, 2 cylinders. There is one cylinder with a piston that's connected to a rod, and we have another cylinder that is connected, that has a piston that is connected to a rod, and they are connected through some sort of a hose. So we have a closed system. Now, when you apply force on this rod, it's going to make that cylinder go that way. There is no angle between these two. It's just going to cause that one to push out. Does it mean that we have the angle between these two? Because that vector is pointing this way, and that vector is pointing that way. So we have an angle there? Philosophically, yes, but we're not philosophers here. Okay, there's this. Okay. We're not philosophers here. We're scientists. We deal with the real stuff. Okay? All right. So, the force that's acting upon the cylinder here is with the same angle of the movement. When we apply the pressure is going to build up in this chamber right here, and it's going to act on that cylinder in this direction, and it's going to move the cylinder in that direction. So for that reason, we can just forget that, because cosine of 0, because in that case the forces are aligned here, forces are aligned here, we get 0 angle between those realistically, and cosine of 0 degrees is 1, so we can skip that. So that's why when it comes to our understanding of things, what we deal with, we just say that work is equal to force times distance, because that is skipped. Alright, unit of work is joule, and 1 joule is 1 Newton meter. When the force of 1 Newton moves an object 1 meter, then we have done the work of 1 joule. If we apply the force of 1 Newton and that thing doesn't move, we have lost energy. I have lost energy by trying to push that, so I'm going to have to make sure that I eat extra sandwich later on. I have lost energy. Where did the energy go? Into heat. Right? So I also have to take a shower, right? So if this thing doesn't move, according to science, no work has been done. A displacement has to happen. So that, again, that's a grade 11, grade 12 physics, right? Right. Okay, cool. So conservation of energy. What does one keep saying here? Get my laser. Hydraulic systems. Well, pneumatic would obey the same rules, but the reason why we mention that hydraulics is because we have tendencies to use hydraulics for power tasks. Okay? The systems, hydraulic or pneumatic, do not create energy. So that's why we have the conservation of energy. Whatever is being spent here is being received here in a closed system. Now we have to use the expression here, work is being done in one container here, one cylinder. I used to say that in one environment and the other, but you see, because it's a closed system, the whole thing is one environment. And in that one environment, the pressure is the same at all times. In all the areas, the whole pressure might go up or down, but if it goes up or down, it goes in the whole system equally. And when it comes to doing work, we can't get more energy from anywhere else. We don't get free energy. Work in equals work out. Do you work out? No, I work in. It's the same thing, right? Okay, funny back. All right, so whatever you do the work here, it's going to reflect on the work being done there. So we have the work equals force times distance. So if we have force applied to that cylinder, it will be force 1, distance 1 would be here. It's going to equal to the same thing on the other side. But if one of the numbers changes, then something else has to change also here in order to keep the equal sign, the equality sign. Which translates to, there's a finger pointing at this thing here, that means it's probably important, right? Large force, if you have to apply large force, it's going to translate into shorter distance, or smaller force, if you use smaller force here, is going to equal to longer distance. What does that mean? Here's a tiny cylinder with fluid in it, and there is a thicker cylinder here, and they're connected with hose or piping. If you, well, in order to displace certain volume of the liquid, you're going to push that thing certain distance, and you're going to, let's say, displace from here to here. You're going to displace that much volume in the cylinder. That volume is going to be transferred into this bigger tank, but if the piston was sitting here with the rod, then this volume here is going to fill that, but because it has more area to cover, it's not going to rise. This is not going to rise as much. However, we gain the force, because just if you look at the formula here, if you have couple numbers here, you make this number bigger, then on that side that number has to be smaller, or that number has to be bigger. So that's how we can lift a heavy load, by pumping things a lot here. And pumping is just adding distance, adding displaced fluid, and we use the check valves in order to, it's just like a diode. Check valve to hydraulics is like a diode in the electrical system. Once you push the fluid in there, check valve stops it from going back, and you just push more and push more and push more, and slowly but surely you can lift a heavier weight. So you can gain the force, or should I say we have a force advantage, at the cost of having to cover more distance on here. So that's basically what this thing means here. Review. Conservation of volume. It's very important. So if you are not here, if you're absent, and if you ask, I was absent, I couldn't come to school, is there anything important that I missed? Yes, you have missed. This is the very important thing that you missed. By the way, don't ever ask that question. Is there something important that you missed? All right. For incompressible fluid, which would be a liquid, the area times the distance of one cylinder. Again, we have the area 2 on the other distance of the other cylinder, and there has to be that equal sign. What does this expression mean? It means that fluid volume pushed in is equal to the fluid volume lifted out. However, if you have a large piston, then you're going to cover less distance upwards. If you have a smaller piston, then you're going to cover more distance. But it's going to be harder to push the big cylinder. It's easier to push the smaller one. So this is the conservation of volume. You see here? This volume that was given out from this cylinder ends up here. No more, no less. Okay, I already explained that to you. Hydraulics versus pneumatics, I might ask you some questions like that. So read these notes, the post-it notes that are there. I will ask you some questions that will be multiple choice. I will give you some questions that will require you to come up with an answer with no multiple choice. That means you have to know. And I will give you some problems to solve that is going to require you to do some calculations. So yes, please bring your calculators. All right, so back to the schedule here. Fluids, liquid or gas. Hydraulics, pneumatics. Associated with liquids, hydraulics. Associated with gases would be pneumatics. Properties. Compressibility. Hydraulics are considered incompressible, and sometimes you're going to see nearly incompressible, but for our purposes we can just consider them incompressible. They cannot be compressed. Pneumatics, we have compressible medium. And these are the two most important, probably two most significant differences in the properties that make the other properties different, slightly different. So the response with hydraulics is immediate because there's no compression. You move one cylinder, the other cylinder moves immediately because there's no compression. The medium doesn't compress. The fluid, the oil doesn't compress. It doesn't have that cushioning. Whereas gases, they are compressible, so you're going to have a slightly delayed reaction. And we call that spongy or springy. Pressure. Not going to expect you to remember the numbers. Just know that because hydraulics are associated with massive force, power, and associated with that precision, just imagine a backhoe with those cylinders sliding in and out. That's oil in them. Backhoe is powerful. A a machine that has suction cups and does some linear motion to pick up sheets of paper on the huge printer doesn't require as much force as the backhoe does, or a bulldozer. So, of course, that means that the pressures will deal with higher pressures or pressure in hydraulics than more pressure, more power, less pressure, less power. But don't be deceived. This here in pneumatics, the pressure is lower than the hydraulics, but as far as the safety is concerned, that thing can very much still hurt us. Okay, so just a little side note, this one is free. As far as the exhaust, with hydraulics we will have a closed loop. With pneumatics we vent this into atmosphere. And let me just see, maybe I kept the notes here from the last presentation. Okay, yeah, I kept those notes. Here's my Photoshop board, writing board. This is hydraulics. So what we have in hydraulics, we have to have some sort of supply of a liquid that would be oil. The oil is being sucked in by a pump, and it's going to pass the check valve, one-way directional valve. So as we push the pressure in, the pressure can't escape back, so we are building it. And here's the big black box, which symbolizes whatever work is being done. And after the work is being done on whatever system it is, that medium is going to be exhausted through a pipe, come back to the reservoir tank, which makes it a closed system. That's what it means. It's a closed system right here. When it comes to the air, we do have a pump here. We might have some check valve going on. And yes, we will have some reservoir tank, but the purpose of the reservoir tank in the pneumatic system is not the same as the purpose of the reservoir in hydraulics. The purpose of the tank is just to keep enough pressurized air so you have the reserve. When you need more, you can just grab it from the tank. The tank is going to, it has the volume of the air compressed, pressurized, and if more pressure is needed, more air is being needed, then the pump is going to work a little bit harder, maybe resupply to keep up the pressure that's in the tank. But it's not going to, if there is more pressure needed at some certain task is being performed, it's not going to go directly and hit the pump. So that's the cushioning that we have. Or cushioning. I shouldn't say cushioning because cushioning is in pneumatics is associated with motion. It's the reserve of the pressure that we have. And once the air is being used to perform whatever the task, through the exhaust valve, through the exhaust vent, or through the exhaust port, it's just being spat out. Where? Into the air. Because it is air. So we don't need to keep it contained so it doesn't contaminate the environment, because the air is the environment. Alright? Now, if you want to get philosophical here, then you can say the whole room is just like the oil tank. Right? We grab the air from the room, we release it to the room, so we are sitting in the huge tank. And our closed system is the atmosphere that is on planet Earth. All right. All right. Moving on. So here, closed loop, or the exhaust is vented to the atmosphere. If it's air. If there's a special situation or special case, maybe some medical lab or maybe whatever else, then we might have to have a closed system for pneumatics. Examples of calculations. Now, here is the quick calculations, but I'm going to ask you to make sure that you write the units in the calculations. Don't do what I did here. I'm going to specify it in the... actually, you know what? I always kept asking you to specify the units, or showing you that I am doing it. All right. What do we have here? There's no any verbal explanation of what this needs to be calculated, but what can we deduct by just looking at it? We have two areas. We have force. We have the area 1, which would probably be a piston, and we have the force that's acting on that piston of that certain area. Can we tell the pressure in the whole system, including the other cylinder that we don't have the force, but we have the area? Yes, we can, because pressure equals, remember, pounds per square inch, so pounds is the force per square inch, psi, and the square inches area. And that's what we have here. This here, there's 200, is the force. That's the F1 here. I'm just going to just give you that a little bit here. F1 over the area 1. That's the area 1. And because pressure is equal everywhere, so we got that. So can we tell the output force on that, which would be the force 2? Yes, we can. We just apply that formula, and we rearrange things a little bit because we just want to find out the force 2. And looking at the proportions, here's the equal sign. We want to find out what this one is, so what do? We multiply diagonally and divide by what's left. Multiply, and the product of that multiplication divide by what is left that we haven't touched yet. So F2 equals F1 times A2 divided by A1. Or you can have that pressure here, so which that was being used. Same thing. You're going to get to the result of the force number 2 equals 10,000 newtons. Does it make sense? Just verify for common sense, because sometimes you might apply the numbers in reverse. Alright. So the first area is much smaller than the second area. And yeah, the first area is much smaller than the second area, and that force applies to the smaller area. So the bigger area is going to end up with the bigger force. It checks out, makes sense. We're gaining the force, but if you look at the other slides, we're going to lose the distance. Alright. Distance calculation. What do we have here? Area 1, so that's a smaller piston. There's the bigger piston. And we know that the smaller piston moved 20 centimeters. How far is going to the bigger piston move? Well, we know it's going to move less. Okay. Remember this formula here? How do we get the distance 2? Distance 2, right here. We have to keep the equal sign, so we take that side divided by A2 just to throw out the distance, and we end up with that. So because of that equation here, that translates into this. Apply the numbers, and here is the distance that the bigger cylinder is going to move. Does it make sense? Always verify. Well, the other cylinder is bigger, the bigger cylinder has bigger area, so it's going to cover less distance because of the, remember, the conservation of volume. It's going to, the same volume that is displaced from the smaller cylinder, it is going to move the other cylinder less up because the volume goes sideways in the bigger cylinder. Right? Remember something here? Let's just do some crazy. Let's go crazy here. What's the? We both have the same units. We just have okay. When you do the calculation, you just gotta make sure that you equalize the units. You can't have one in meters, the other one in centimeters. They have to both be the same. So area 2 divided, okay, what do we have? Area 2 divided by area 1, which in our case we have 0.1. I'm going to skip the units for now here. And this is, well, 0.002. .1 divided by, we got 50. All right. That's our multiplication factor. That's our multiplier. Now, let's see if that checks out. Then we should have some. Now, the distance is longer in the smaller cylinder than the bigger cylinder, so we're going to have to see if, where's my pen? Here it is. Then that should give you, it should give us 20 centimeters divided by 0.4 centimeters. I wonder what that's going to be. 20 divided by 0.4. Oh wow, magic, right? Okay, there we go. All right. Required force, another, so it has to do with pneumatic design or hydraulic design, right? Required force is, okay, what do we have? Force, we have 4,000 newtons, and the pressure, so we need to see how big the other cylinder is going to be. All right, we got to know that the pressure is common, and the pressure equals force over area. And from that, Pascal's law, we can derive this formula here, because we're trying to find the area. We got force, we got pressure. Wow, this is simple. We got 80 centimeters squared, or 80 squared centimeters here. So this one is simple. What's just notice that you have 500,000 pascals, or pascals. And in the bracket, they just say, by the way, it's 5 bar. Because 1 bar is 1 atmosphere, and 1 atmosphere is 100 pascals. Sorry, 100 kilopascals. 100,000 pascals. Huh? Just to check up questions here. Why does hydraulic system not violate the conservation of energy? Because work 1 equals work 2. I would encourage you to analyze that. There we go. And work is force within a distance. Work 1 equals to work 2. Work here, same work here. We don't gain energy. So that's why, okay? There we go. All right. Why are hydraulics better for lifting cars than pneumatics? Well, this one is easy. First, actually, you know what? Can somebody come up with the answer here? There are more than one reasons. There's more than one reason. I just want to see if you guys are awake. Why are hydraulics better than for lifting cars than pneumatics? There's that uncomfortable silence. All right. Then I'll leave that for you to find out. I might ask you the question here. If somebody speaks out, I'm going to elaborate on that. If not, then that means you know it. All right. What physically causes pressure to act in all directions? And that was right here somewhere. Is it? We have that one, the first slide here. Here it is. A fluid, the properties, because of the properties of the fluid. Fluid has no fixed shape. The particles flow freely, so they just fill up every little corner and they press equally on every point of the container. What physically causes pressure to act in all directions? It's the fluidity of things, because the particles are not bonded together as they would be in solids. Hydraulic piston has areas. Okay. There are two pistons here. One with the area of 4 square centimeters, one of 80 square centimeters. What is the multiplication factor? We just did that. Pressure is equal everywhere the same. Where's my pen here? Pressure is equal the same everywhere. And pressure equals force over area equals force over area. 1, 2. Huh? So in order to keep the equal sign, we can keep the equal sign by saying this. Look, we can rearrange that. We can just turn it around, kind of a little bit turn it the whole thing on their side, on each side, and we could just say What am I doing? A2. Getting A2 over A1 equals force 2 over force 1. Well, look at this here. 80, that's the 4, that's the area 2. 4, that's the area 1. 80, just divide the areas. Divided by 2, and I'm going to spare you the mouse clicks with writing the units. Sorry, 4. That's the one right here. And that gives us 20. And of course, because it's a centimeter squared and there is centimeters squared, these are going to cancel out, so the multiplier is unitless. It doesn't have unit. So the multiplication factor here is 20. If, there's the other question here, if an input piston moves 30 centimeters, how far does the output is going to move? Well, what we're going to see is the output area bigger or smaller. The output area is bigger, which means it has to move less than 30 centimeters. How much less? We already have the multiplication factor here, right? 30 divided by 20. That is going to give us 1.5. So, centimeters. Why? Because here's 30 centimeters, and the 20 here that has no unit, so we are left with centimeters. It moves less. So with those area differences, these are going to be the difference because we found the multiplication factor or the multiplier. Given the pressure and force, can you solve for the... I'm not going to torment you with that question tonight, but I might give you that question on the test. Just have to remember what the formula for the area is, so you're going to have to perform some extra steps. But you're going to apply this formula. Okay? One sentence summary of that thing. Okay, well, Pascal's law allows us to trade distance for free. Pascal's law allows us to trade distance for force by transmitting pressure equally through the confined fluids, enabling the hydraulic and pneumatic systems to perform work efficiently without creating energy. Because whatever work is done on one cylinder, same work is going to be done in another cylinder. These unit conversion shortcuts, I'll give you those too. What does it say? These unit conversion shortcuts students use under time pressure. That'll be a test, right? That these are not the full derivations. All right. Pressure You have the conversions for pressure, psi into kilopascals. Here you go, that. Force, kilograms or grams or kilograms, and Newton force. Mass. What's the difference between mass and force? Mass is force, but within our gravity. And they're exchangeable with numbers. Engineering approximation used on tests. Yeah, okay. Force in newtons equals mass of kilograms about times 10. Pounds into newtons, 1 pound approximately equals to 4.45 newtons. Area conversions, distance conversions. When I posted, you can analyze that. And here's the work or energy. They're both measured in joules. You can lose energy, you can dissipate energy, but work might not be done. All right. So, but they're both measured in joules. So here's the conversion. Quick units check. Quick units check. So here's a statement and a half. Like for example, when you go kilopascals times meters, square meters, that's going to give you newtons. Newtons divided by square meters is going to give you pascals. So if you keep writing units, and if you stick to that, that is going to give you the proper units. So if you do a long calculation, and then you work out those units, and you get the volume in let's say centimeters, then probably for sure something got messed up along the way, something got skipped, or there was some kind of an error along the calculations. So you have to retract your steps to see what went wrong. But also there's another statement here. If units cancel cleanly, which means after you do the cancellations and all those combinations, that it comes up to the proper unit, like for example the area gets in square meters, then your setup is correct. The setup meaning all the steps in your calculations. So skip no steps. Even if you're dividing by 1, that 1 has a unit, which is going to help you. I don't have to explain that to you, right? And here's another caveat here. I hate that word, but I just said that. Probably correct, because you can still come up with multiple errors, which is going to give you, by some sort of coincidence, the proper unit, but there could be some errors there, right? Boom. Now, the other thing, I'm going to show you the little formula sheet that I have almost finished preparing for you. Where's my... Here it is. Here, extracted that from the PowerPoint presentation. Formula sheet. For pressure, for work, force. These are all the formulas that have been used in this PowerPoint presentation that I gave you during week 2 or something like that. And I know these are all the formulas because I gave the commands to PowerPoint to extract all the formulas. So there it is. Right? I'll give you that sheet. I'll just kind of compress it a little bit better. And I'll give you the unit conversions as well. By the same token, I'm encouraging you to create your own formula sheet. I also might ask you something like this. Where's my thing here? Do I have it? Where did it go? I don't know where it went. Well, that's a zoom. That's another zoom. That's still the zoom here. I'm going through my... there you go, I have it. I might ask you something like this here. Things about the ports. What makes a 3-2-way valve a 3-2-way valve? Would this be a monostable or would it be a bistable device? I'm asking, does it look like it's a hydraulic or does it look like it's a pneumatic valve? What type of actuation this valve uses? Like, for example, this is a solenoid. That's a symbol for the solenoid. But I might draw push button. I might draw a momentary push button. I might draw a maintained push button. Right? So, and port 1, what would be the designation of the ports? If this is port 1, port 2, that's the main powertrain of the main airflow. 3 is exhaust. We know that. What would be the port 4 and 5? They are not just numbered randomly. They do have some organized way of designating things. So I might ask you things like that. Yeah. I might ask you the type of switches. What's a single pole, single throw mean? I might ask you things about the relays that we talked about. What makes a relay work? What's an EMF? What's a back EMF? Everything that we... I might ask you a question like that. I might give you a question. So, we got a week to review. And if you, by the way, I'm available. If you do have certain type of uncertainties, you need some further explanation, by all means, shoot me an email. Or ask me during the lab. We're going to have labs tomorrow. Sections 1, 2, and 3. All right, that's it for today. We went overtime a little bit, but I just want to make up a little bit for that for the last session that we missed, which is basically what I just went over here. It's just the other guys got it twice, but you can watch the video again here, so you missed nothing. And that's it for today. Thank you for your attention, and I will see you when I see you. And yeah, I'll say good night. I'm tired. I think I'll go home now.